Today we will analyze the response of an RC circuit when the input is bipolar current pulse train. Consider an RC circuit. Resistor is 1 kilo ohms, capacitor is 1 microfarad. The input current source is a square pulse with height 5 milliampere. On time is 5 milliseconds, off time is 5 milliseconds. Now for a bipolar pulse train, the height would swing between plus 5 milliamperes to minus 5 milliamperes and plus 5 milliamperes during on time and minus 5 milliamperes during off time. Since R and C are in series, the capacitor will charge and discharge accordingly. We want to find the voltage across capacitor, voltage across the resistor and the current flowing through the circuit. This is the input current that we are feeding to the RC circuit. Now to calculate the voltage across capacitor between 0 milliseconds to 5 milliseconds, the input current is constant 5 milliampere and the capacitor starts charging linearly and the voltage across the capacitor can be calculated using this equation. Now at 5 milliseconds, the input voltage would have charged to 25 volts. Now between 5 milliseconds to 10 milliseconds, the input current is minus 5 milliampere. On substituting it, we can see that the voltage across capacitor at 10 milliseconds is 0. We have considered this initial voltage. During 0 to 5 milliseconds, the capacitor has charged to 25 volts. We are considering that initial voltage here and on adding with minus 25 volts, we get voltage across capacitor at 10 milliseconds to be 0. This is how the graph for the voltage across capacitor looks like. At 5 milliseconds, it is 25 volts and at 10 milliseconds, it has dropped down to 0. The nature of charging is linear and the nature of discharging is also linear. Now from 10 milliseconds to 15 milliseconds, again input current is 5 milliampere and it is available and the capacitor now charges linearly to 25 volts with 0 volt being the initial value. 15 milliseconds to 20 milliseconds, the input current is minus 5 milliampere and the capacitor voltage drops to 0 volts. The voltage across resistor can be calculated by multiplying input current into resistor and the current flowing through the circuit will be same since R and C are in series and it can be calculated by using the equation VR by R. This is how the voltage across resistor looks like and this is how the current flowing through the circuit looks like. These two look similar because current flowing through the circuit is calculated by dividing VR by R. Here we have calculated directly at 15 milliseconds and at 20 milliseconds. Let's take different time steps within this 10 milliseconds to 15 milliseconds and see how the voltage across capacitor rises to 25 volts. Now to capture the precise charging profile of the VC and the voltage across resistor and current flowing through the circuit, the calculation is repeated in Excel with more finer time intervals of 200 microseconds. Let's look at that. Here the on time is 5 milliseconds, off time is 5 milliseconds. This is the input current that we are feeding to the RC circuit. From 0 to 5 milliseconds, the voltage across capacitor can be calculated using the equation I into T by C plus V initial. This is how the voltage across capacitor looks like and the voltage across resistor can be calculated using VR is equal to I in into R. And the current flowing through the circuit is VR by R. This is how the input current when fed to an RC circuit has transformed the voltage across resistor, voltage across capacitor and the current flowing through the circuit. Consider the case where T on is much greater than T off. T on here is 7 milliseconds. This is the input current that we are feeding to this RC circuit and the voltage across capacitor at 7 milliseconds is calculated to be 35 volts. Now between 7 milliseconds to 10 milliseconds, the input current is minus 5 milliampere and the voltage across capacitor is calculated to be 20 volts at 10 milliseconds. Now here we can see that the capacitor's voltage has not completely fallen down to 0 because the time period is only 3 milliseconds when the input current is minus 5 milliampere. If the on time was equal to off time, it would have fallen completely down to 0. Let's look at the voltage across the resistor and the current flowing through the circuit. Voltage across resistor can be calculated using I in into R and this is how the graph looks like and the current flowing through the circuit is calculated as follows. The on time is 7 milliseconds and the off time means when the input current is minus 5 milliampere. It can be considered as T1 and T2 as well. It is 3 milliseconds and this is the input current that we are feeding to the RC circuit and this is how the voltage across capacitor looks like, voltage across resistor, and the current flowing through the circuit. These values are calculated using the same equation that we discussed when the case is T on much greater than T off. Let's consider the case where T on is much less than T off. T on is 4 milliseconds. This is the input current that we are feeding to the RC circuit, and T off is 6 milliseconds. Now the voltage across capacitor can be calculated using this equation. Time period is 6 milliseconds when the input current is minus 5 milliampere. The capacitor's voltage has reached negative, and this is how the voltage across the resistor looks like. This is how the current flowing through the circuit looks like. Here, time period when input current is 5 milliampere is 4 milliseconds, and when input is minus 5 milliampere, the time period is 6 milliseconds. This is how the voltage across capacitor looks like for the input current that is being fed to the circuit, and this is the current flowing through the circuit, and this is the voltage across the resistor. Let's simulate this and check. Here we have considered the case where T on is equal to T off. On simulating this is the input current that we are feeding, this is the voltage across the capacitor, this is the voltage across the resistor, current flowing through the circuit. Here is the summary for the case where T on is equal to T off. This is the input current that we are feeding, and this is how the input current has transformed the voltage across the capacitor, resistor, and the current flowing through the circuit. If the time constant of an RC circuit is comparable to the input's time period, then it will not resemble the behavior for bipolar current pulse train input. Thank you for watching this video.